Okay, students, good morning. So, this is our second lecture of laser. In the first lecture of laser, I talked about some of the properties of laser which were very important in devising a device like laser, which is highly monochromatic. It emits very high power and it is highly monochromatic also. Okay, and the another important property is the directionality. So, because of high directionality, its divergence of the beam is very less and it can be sent from one point to the another point without much loss in the laser lights. So, we talked about all those properties of the laser and then we talked about the possible transitions if the two levels are available to us, for example, the ground state and the excited state. I told you that there are total three types of transitions that are possible and these transitions are responsible for the lasing action. So we need to understand the basic physics behind this laser device and the full form of laser is the light amplification by stimulated emission of radiation. So the name itself suggests that one of the possible transition type is there in the laser. But all the three transitions are taking part in the laser action because in order to communicate with the laser, we need to give these three possible transitions. Okay, out of which the third transition, that is stimulated emission of radiation, is very important and it was given by Einstein in 1970. So here you can see that in this particular slide in our syllabus UPH 004 we have to talk about the basic concept behind the laser, then the laser properties, then there are three lasers that we need to discuss. One is the ruby laser. It is a solid state laser. Then we have HENE laser, which is a gaseous laser, and the another category that is called semiconductor laser. It is also a solid state laser, but it is kept under a different category. Okay. Then we are going to talk about some of the application of the laser, and the important one is the optical communication. Okay. So let us start with the second part of this laser, and we will see one by one the uh, related concepts. Okay, so before coming to this, I will just I'm interested in recalling the points here. I told you that there are three possible transitions here. Just have a recall on this. The first transition is when the electron is in the ground state. So the only possibility for this electron to go to the excited state, provided a particular energy, which is the difference of the two energy level, is incident on this particular electron. So electron will jump from the lower level to the excited level. Now, once it is reaching to the excited level, there are two options that it can come down. One is by completing the lifetime in the excited level, it can come down, and that is being done by its own, and that is why it is called as spontaneous emission, because it is going to emit a photon, and that emission of that photon will be equivalent to the energy difference between the two levels. But since the electron has completed the lifetime in level E2, this will be called as spontaneous emission. The third and which is very important transition is the stimulated emission. That means it can also come down before completing its lifetime by incidenting a photon on it, and it will be stimulated to come down to the ground state by emitting a photon, and that photon is going to get added up with the initial photon, and the energy of the out, out, outgoing photon will be something higher than what we have been incidenting. Is that okay? So this particular transition is stimulated by a particular energy in the form of photon or in the form of other things, in which the electrons not can go up but it can come down to the ground state, and it is going to emit in the way that you can see that two photons, one which is incidenting it, that will also come out, and the another photon is because of the difference between these two. That means the two photons will have a channelized energy in the form of this kind of photon. So you can see that the wavelength and the wave amplitude distribution is different in this particular wave as compared to all of the other photons. Is that okay? So this is what we have done in the earlier lecture, and now I'm going to come to this particular part. I told you two terms. I told you about one term that is called pumping and another is population inversion. I told you that whenever there is a system and there are atoms in the ground state or electrons in the ground state, you can pump them. You can pump them to go to the excited state. That can be done either by providing external energy in the form of heat, light, or some other means. And that will be helpful in bringing the atoms from the ground state to the excited state. So whenever the atoms or the electrons are going from ground state to the excited state, that process of bringing the atom from here ground state to the excited state is called pumping. Okay, so pumping is a process, and that process can be done by providing the external energy. Now once the pumping is done, there might be a development of an extra level, you can say a metastable state. We till now we have just talked about the ground state and the excited state, but I told you that as soon as the excited state's lifetime is over, they are going to come down to the ground state. Now what we are doing is we are talking about an extra metastable state which is in between the ground state and the excited state, but the lifetime of that metastable state is much larger as compared to the excited states. That means even if the lifetime has been completed in the upper state, the electron will not go down to the ground state, but they can reside at somewhere in between the two levels, and that level will be called as metastable state, which is having much higher lifetime as compared to this. That means they can stay here for longer time as compared to the excited state. So this particular point where an excited state has been populated largely as compared to the ground state or the excited state, that particular state is called population inversion. Okay, so whenever, in other way you can say that whenever the excited state is more populated as compared to the ground state, that particular state is called the population inversion. So population inversion is a state and pumping is a process. Okay, so what is the importance of metastable state? The importance of metastable state is here, that once the population inversion has been reached, the lasing action of a laser is simple to achieve. That means this is the best situation where we can achieve the lasing action, because there the all the electron that are populated in a particular level can simultaneously come down to the ground state, by incidenting them with the external energy and stimulating them to come down to the ground state. So this kind of emission which they are emitting the photons, this particular emission is a type of stimulated emission and not the spontaneous emission. So from here to here, they may come down and there might be the emission of heat or energy in the form of photon. That will be because of the spontaneous emission, because they are completing their lifetime much before the lifetime of this particular level. So they are going to get accommodated, populated in this particular part, and simultaneously after some time, if you are going to incident them with the external energy, they will get stimulated to come down to the ground state, and this process is called stimulated emission. And this process, which is I'm telling that stimulated emission, leads to the lasing action. So laser can be emitted from this because there might be millions of electrons that may come down to the ground state simultaneously by emitting millions of photons, which will be having same energy, same similar properties, and that is where we can get a beam of light which is highly intense, highly coherent, and highly monochromatic. Is that okay? So this is one of the importance of the metastable state, and that is why we like to create metastable states whenever we want to devise any laser device, because metastable state helps us to create a particular state from where most of the atom or the electron can be simultaneously brought back to the ground state by emitting millions of photons and then reach achieving the lasing action. Is that okay? So the atom in the metastable state E2 are bombarded by the photons, as I told you, of energy h nu, hf or h nu, E2 minus E1, resulting in an incident and induced emission. Okay, so they are stimulating the emission. That is why they are called as induced emission, and this gives an intense coherent beam of light which is coming out in a particular direction. So they are highly directional also. Is that okay? So let us move ahead. Here is one of the equation, and that is called Boltzmann equation, and according to this equation, if we assume that there are n1 number of electrons in the ground state E1 and n2 number of electrons in the upper state, any upper state, excited state E2, then there is a tendency that E1 will always be populated more as compared to E2. That means N1 will always be much large as compared to N2. That means under normal thermal equilibrium situation, always the ground state will be much more populated as compared to the excited state. That means in normal circumstances, you can never achieve lasing action. For lasing action to achieve, you need to create a state of population inversion, which means that N2 must be larger as compared to N1. So here he is telling that delta E is E2 minus E1, the energy difference between the two energy level. So the energy level between the energy difference between the two energy level is much larger as compared to KT. Okay, T is the normal temperature at which we are talking about. So thus in the equilibrium, the population of the higher state is very much smaller and than that of the ground state, and as a result of this, stimulated emission is very less. Okay, stimulated emission possibility is very less. So what we need to do, we need to create, or we need to change the temperature of the system in such a way that that condition can be brought whereby most of the atoms or the electrons can reside in the excited zone. Okay, so if somehow we can make N2 must to be greater than N1, so then in that particular case, process of stimulated emission dominates and laser action can be achieved. Okay, so this relation you should remember. Okay, fine. Okay, so this is the relation. Now let us move ahead. There are certain categories of the laser depending upon, as I told you, that there are three components of the laser. The first component was active medium. Then I told you that there is a pumping source in all the lasers and there are resonators in all the lasers. Now, depending upon what kind of active medium they have, they can be categorized in a different category. Okay, so here you can see that many classifications are there, but if we are talking about the category depending upon the active medium can be gas, solid, liquid or semiconductor, and based on that they will be called by their name. That means gaseous laser, solid state laser, liquid laser or semiconductor laser. Okay, so depending upon the active medium they can be classified into four parts, and these are the four parts. Now depending upon the power which we are using, either to pump the system or otherwise to provide the energy to the system. So there can be a low power lasers, there can be intermediate powers lasers, there can be some lasers which need very high power. So depending upon the power need, we can classify them in these three categories. According to the wavelength, as I told you, that whenever the wavelengths are emitted, generally we see the red, blue, green colors in the disco threat also, and these lasers are in the visible range, but there is certainly a possibility to create the lasing action not in the visible region but in the other regions like ultraviolet or infrared. So depending upon the difference between the energy level and the corresponding wavelength they are proportional to, we can have E2 minus E1 to be equal to Hc by lambda. So lambda is going to be in the range of infrared or ultraviolet, and if visible then it will be able to, we can see them. Okay, So according to the output nature of the emission, there might be a possibility that whatever the light, the laser light that is coming out of it, it is continuous. Okay, so those lasers are called as continuous lasers. And if the light is not coming continuously but in the form of pulses, so then they will be called as pulsed lasers. Okay, so the point to note here is that the classification can be made based on many things. So you have to understand that on what basis you have to classify the laser. So depending upon that, you should be knowing that what are the different kind of lasers. Okay, so according to laser technique, contact and non-contact. Okay, so these are the categories. Now I'm just naming them, some of the lasers that is there, just all of you to remember. So according to active medium, gaseous lasers are HENE laser and CO2 laser, carbon dioxide laser and HENE laser. So one of the laser we are going to see here itself, and the second laser is the carbon dioxide laser. Now the another one is solid state laser. Again we are going to see the ruby lasers in our lectures. The another example is ND-arc laser. Okay. Now liquid lasers are the dye lasers, and these are in the form of dyes. So pulse dye laser, they generally emit the light in the form of pulses. So pulse. So that is why they are called as pulse laser. Semiconductor lasers are called as diode lasers. Okay. So let us move ahead again. Now here is something which is very important to understand, and they are generally called as three level laser and four level laser. Okay, three step laser and four. You should understand in this way that we have two kind of laser. One is three level laser and the another is four level laser. What is the difference between them? So here you can see that there are 1, 2, 3 levels. Okay, 1, 2, 3 levels, and here 1, 2, 3, 4 levels. So 4 means, does not mean that there has to be only 4 levels, it can be higher than that also. But just to simplify in your understanding, they are given 4 levels here. But what is the basic difference between 3 level and 4 level is what I am going to tell you. Just look at this point. This is the ground state. Okay, this is the excited state, and this is as usual the metastable state. So, whenever the lasing action happens between the metastable state and the ground state, whenever the lasing action or the stimulated emission of radiation happens between the metastable state and the ground state, then those lasers are known as three level lasers. Okay, those lasers are known as three level lasers. But whenever the stimulated emission of laser or lasing action is happening between the metastable state and some state which is not the ground state but above that, okay, that means laser light is coming out because of the transition between the two levels. None of those levels are the ground levels. When the ground level is not involved, that particular level is called four level laser. And whenever the ground level is involved in emitting the lasing light, then that particular level is called as three level laser. Is that okay? So whenever you see that ground level is involved, you call that laser to be a three level laser, and whenever ground level is not involved in the transition or in the stimulated emission of radiation in the form of laser light, then it is four level laser. Okay, so this is the difference between three level laser and the four level laser. So you can see that we have two levels, E1 and E2. So we don't have any option. We have to pump it. We have to find the lasing light. Here you have created a metastable state, E1, E2 and E3. So you are pumping them to the excited state. Rapid relaxation means after completing the lifetime they will come down to this state, and after that they will be populated here and they are going to create the lasing level. Okay, so generally this is called three level laser. Okay, this is two level laser, nothing is there, metastable state is not there. Okay, so this is three level laser. Now what is four level laser? Whenever you have the rapid relaxation in a particular metastable state and they are coming down not to the ground state but to the another state which is above the ground state. So this kind of lasers which are giving you the lasing action in between the states of the excited and the ground state. So then in that case they will be called as 4-level laser. Okay, so here a note is there that true 2-level laser system cannot produce a population inversion. So it is not possible to create a population inversion state in the 2-level system. So that is why we never take this kind of system for lasing action. So the best system is the 3-level system and the 4-level system. Why? Because it is very easy to create population inversion state, because the metastable state is populated or can be made populated as compared to the excited states, because they are having very less lifetime, and the atoms or the electrons will definitely come down to the ground state after completing that lifetime. So you will not be able to achieve the population inversion. Okay, so can we sustain a population inversion in a given laser? Yes, definitely we can sustain by allowing some of the incident or allowing the system to be getting incidented by some external source of energy, so that as soon as the electrons are reaching to the ground state they can be directly pumped to the excited state. So we have to provide the external energy so that the electrons should not populate this point, but it should directly pump those electrons to the excited state, and the population of E2 level or here E3 level can be enhanced. Is that okay? So a 3-level laser must be pumped harder than a 4-level system, and that means more molecules must be pumped into the excited level to produce the lasing. Is that okay? Now you can see here that there is the two lasers which we are going to do. You should understand where they exactly can be classified, how they can be classified. So here ruby laser is the solid state laser. I just told you it is a 3-level laser. You have to remember this 3-level laser. Then it is not a continuous laser. It is a pulse laser. That means you cannot expect continuous supply of the laser light from that particular laser. Okay. So what kind of pumping we are using in ruby laser? It is optical pumping. That means we are allowing the external photons to pump the electrons from the ground state to the excited state. Okay. Then coolant is required. Why coolant is required? Because we are using optical pumping, the system gets heated up very fast. So we need coolants to cool the system. And the power output is very large. High power of 10 kilowatt can be expected from the ruby laser. Okay. So there are many benefits of ruby laser, except that it is a pulse laser. Okay. Now here HENE laser, which is a gaseous laser, is a 4-level laser. It is a continuous laser, but power output is very low. You can see that 0.5 to 5 milliwatt power is coming out. Coolant is not required, and there is a pumping which is not optical or heater, but is a kind of electronic pumping. You'll just see how what do we mean by the electronic pumping. Is that okay? So these are the specification of the two lasers that we are going to do in detail.